So in this video, we shall be trying to prove the work energy theorem. How does this state? The work done by a constant force in moving a body from one point to another is equal to the change in the kinetic energy of that body there. So we shall try to prove that work done is equal to the change in the kinetic energy. So assuming that we have a body A, this body is acted upon by a constant force capital F, and as a result, the body accelerates at a rate A, changing its velocity from u meters per second, for example, maybe to v in meters per second, and as a result, it covers a displacement s in a given time t. So from the expression of work done, that work done equals force times the distance moved in the direction of the force. From this, we have to create it in such a way that this is the same as the change in the kinetic energy. How to do that? We try to relate what we've been learning before, and using the equations of motion. From the second law of motion, the resultant force F is given by the mass of the body times its acceleration. So that is from the second equation of motion. I call this my Roman 1, equation Roman 1. And then also from the third equation of motion, that v squared is equal to u squared plus 2as. If I make s subject of the formula, I'll simply have that my a is the same as v squared minus u squared out of the 2s. So this is my Roman 2. So what I'm going to do, I'm going to substitute both of these two equations into my equation for the work done, and I'll simply say that my work done, therefore, is given by F, which is equal to ma, then times the s. And where there is the a, I'll simply put my m times the v squared minus u squared out of 2s, everything times the s. And this is the same as the s cancels out. I'll end up with a half into m v squared minus u squared. When you look at this expression closely, you'll simply see that work done is the same as the final kinetic energy minus the initial kinetic energy. And really, this is the same as the change in the kinetic energy of the body here. Now, remember that in our applications of this, in case there's any other force acting on the system, then you have to cater for that as well. For example, in case a body is pulled along a rough ground, you simply say that total work done at point A must be total work done at point B, or total work done at A is equal to total work done at point B. We shall be seeing this in the examples to follow, but as per now, the proof is given by that.